In this video, we're going to talk about enthalpy changes and specifically calculations using Q equals cmΔT or mcΔT. Okay, it doesn't matter which order you put the three values in. And specifically, we're going to concentrate on combustion, although Q equals cmΔT can be used to do calculations on neutralization and on endothermic reactions and things like that, but they'll be gone over in other videos. And before we talk about Q equals cmΔT, we need to remind ourselves of combustion reactions. Now, combustion reactions are a type of exothermic reaction. So here we have an enthalpy diagram with progress at the bottom, and then we've got enthalpy here. And we've got methane completely combusting, and we'll talk about that in a minute, in oxygen. And you can see that the activation energy is this arrow here. And there you've got your bonds all broken and your intermediate. Okay, so that's your breaking bonds, energy taken into break bonds. And then the energy goes down, down, down here. And that's the energy given out when the bonds are made, or making bonds. You can see the energy given out is much larger than the energy taken in. And what happens here is the breaking bonds, if there's a calculation about this, and you'll do this in another video or in a lesson, you can see that the overall enthalpy change is the bonds energy taken into break bonds, or bonds broken, minus the energy given out, or bonds made. If I take this smaller number and minus this much larger number, I'll get an overall negative result. And you can see here negative delta H. That's what we'll have because the products have less energy than the reactants. So if you imagine this as 0, it's gone down. So we've got that negative value. So anything with a negative value in terms of its enthalpy change is going to be an exothermic reaction. And we'll see an example in the next slide. But for now, let's just remind ourselves of this exothermic. Energy is given out to the surroundings. That's the chemical energy within these chemicals. And then the temperature of the surroundings goes up as a result, because all this energy here is given out to the surroundings, okay, and warms them up. And then the energy taken in to break the bonds is much less than the energy given out when the bonds are made. And your examples are combustion, as we've got here, or respiration in our cells and things like that, okay, and neutralization, which is in another video. Now let's go now onto the enthalpy change of combustion, which is denoted by delta CH. Definition is required for you to know for your exam. And you can see here it's the enthalpy change when 1 mole of a fuel is completely burnt in oxygen under standard conditions. We're going to go through all of that at the moment, but notice it's a general theme with all definitions. 1, they tend to be at their standard conditions, and 2, it is about 1 mole. So you've got 1 mole here, and there's 1 mole there. All the definitions are based around this 1 mole of whatever it is. So it's 1 mole of a product, or 1 mole of a fuel, or 1 mole of reactant, or something like that. The only one that isn't based upon 1 mole is the enthalpy change of reaction. That just is a general term for any reaction, and the enthalpy change within that reaction itself. Everything else is based upon 1 mole. So here we have our 1 mole of ethene, and we're combusting it in oxygen. And we know it's completely combusting here because we're creating carbon dioxide and we're creating water. Okay, so if we created carbon monoxide and we created water, then we know it was partial oxidation, okay, or incomplete combustion. Okay, so here again you can see your minus delta H. Now, if you have a number, you've also got to quote it as delta CH and then put the minus by the number, not the minus here. Okay, so anyway, let's go a little bit further into this and look at standard conditions. So standard conditions are something you have to memorize. So specified temperature, 298 K or 25 degrees Celsius, and you've got a standard concentration of 1 mole per decimeter cubed. Pressure is 100,000 pascals and 1 atmosphere. So let's put that in the middle and emphasize that. So what you need to do is you need to have this on a flashcard if you're going to revise for this, and you need to turn it over and then see if you can remember and then put it back. Okay, because this is a memorize part. Just memorize it. Okay, and this is slightly different to RTP. RTP, the only thing that changes for RTP is the temperature and pressure of the room, which is generally very similar to this. Very similar. Usually the temperature is a little bit lower, but everything else is very similar. So now we know the enthalpy change of combustion and the definition, we're going to go on to doing the energy calculation. It's done a little bit like this. So you will do this practical in school, okay? And it's really, really important that you know how to do it and do the calculation. So first of all, we have this copper calorimeter, which calorimeter just basically means it's like a beaker made of copper. And what you have is your thermometer, which you can also use as a stirring rod, because this would need to be stirred all the time. And then you have your water, which you're going to heat up. Now, first of all, before we show you the rest of this, why are we doing this? So we've got specific heat capacity. So specific heat capacity is, and if you follow my finger here on the units, that's really important, joules per gram per Kelvin. So if you think about that simply, it's the number of joules that it takes to raise 1 gram by 1 Kelvin. Okay, 1 Kelvin is equal to 1 degree. So basically, if it's simpler in your head, think of that as 1 degree Celsius. But it is 0.38 joules per 1 gram of whatever that thing is. In this case, it is copper by 1 Kelvin. So if I wanted to heat this 1 gram of this copper up by 1 Kelvin or 1 degree Celsius, it would be 0.38 joules. That's not a lot. That's hardly anything compared to that. So less energy is needed to heat up 1 gram of copper, and more energy is needed to heat up 1 gram of water. So why is that important? So why is that important? Is because when we do this practical, we have a spirit burner. So the spirit refers to the fuel that's inside of it. It's usually an alcohol, but can be an alkane, but it's usually an alcohol. Now, we burn this and we want to transfer the energy into the water. So that energy first has to heat up the copper before it goes into the water. Now, if the copper only takes 0.38 joules to heat up, then most of that energy from this flame, from this reaction down here, is going to go straight through the copper into the water, which is why you use copper. This is also why central heating pipes are generally made of copper, so the heat comes out of the pipe straight away and into your house. Now, if we look here, we can see that the whole setup is designed so that a lot of energy goes through the copper, and then actually it takes much more energy to heat up the water. So that means the energy stays in the water as well. It doesn't get lost as quickly, which means you get a more accurate result. But let's have a look at this and say, well, why, and this is more of an exam question that you're going to get asked, is why does this all sometimes not work very well? In fact, all the time doesn't work very well, and this is a common question in the exam. So think about it. We are not putting any barriers down the side here. So that means a lot of the energy is just going like that and just going outwards and not going into the water itself. Okay? So the issue with the enthalpy change and having it not work very well and actually be much less, and we'll go through that in the calculation, much less than you would expect, okay, is because one, there might not be enough oxygen. That's shown by the fact you've got an orange flame, not a blue flame, and you'll see an orange flame when you do this in there, and that releases less energy. Heat loss to the surroundings, as I've already mentioned, a lot of this heat is going to go this way, it's not going to go up and in, it's just going to go out. If you want to test that when you do the experiment, just hold your hands around about here, and your hands should feel warm. Well, that means the heat energy is going outwards and not straight up. Way to sort that out is to put a heat barrier here, like a heat-proof mat or something around it, and that will improve it and make more of the energy go into the water. There is another one which is a standard answer in the exam, which is it's not done at standard conditions. So if you're going to do enthalpy change of combustion, that means it's done at standard conditions, okay? And this won't be done at standard conditions in your classroom. For example, it won't be 25 degrees Celsius. So those are the 3 exam answers that you need to remember, okay? If you're ever asked, why is the enthalpy change of combustion lower than you would expect it to be? And it's because less heat is transferred into the water, and that affects your calculation, okay? So it's really, really important that you memorise all 3. Before we go on to the actual calculations, it's good to know how you can accurately measure the enthalpy changes. Now, you're never going to do this in the lab because it's an expensive bit of equipment, but it does show you how you can look at those problems with the experiments and fix them all. So, first thing is, think about when you're looking at this, how does it fix the problems? Well, the first thing is it puts it in an oxygen atmosphere, so therefore it's complete combustion. It then has the water surrounding the entire thing. And because the water surrounds the entire thing, all that energy from that reaction is going out. As well as that, we've got an insulating layer around the outside, which stops all the heat going out as well. Another really good thing is that there is a stirrer there. That means that dissipates and spreads the heat all the way through, so you get a uniform temperature. Okay, and the whole thing is controlled, so it's at standard conditions. So it's a great way of getting an accurate enthalpy change. Use a bomb calorimeter. We're now going to go through how to calculate the enthalpy change of combustion delta CH. And we're going to do that by determining the amount of energy given out by the fuel into the water in this copper calorimeter. Now we do that using the equation Q equals mc delta T, and that's the energy transferred, which is in this unit joules. Okay, really important you remember that, it is joules. Then the mass of the water, which is in grams, okay, and that is easily found out because the density of water is 1 gram per centimetre cubed. So 1 gram per centimetre cubed. That means 1 centimetre cubed equals 1 gram. So if I have 100 centimetres cubed in here, I have 100 grams. We also have the specific heat capacity of water, 4.18 joules per gram per Kelvin. Remember that's in your data sheet, so just copy the number over. And then you have the temperature change of the water. That will also tell you whether this is an endothermic or exothermic reaction. If that goes up, it's an exothermic reaction. If it goes down, it's an endothermic reaction. Now in this case, obviously, because we're burning a fuel, it's going to be an exothermic reaction. Now let's put that over to the side and look at the question. Now the question itself is about propan-2-ol, and we've got the mass of the fuel burning before and after heating, which means the difference between these numbers must be the mass of the fuel which we have burnt. We also have the initial temperature and the final temperature, which means I know the temperature change, and you can see it's going up from 20.5 to 57. Also, we are given 100 centimetres cubed here, which tells us the mass of our water, which is 100 grams. So we've got all this information. Let's start putting it into an equation. Let's pull this to the side, give ourselves some space again. So I'm going to start off with the first of our equations, which is Q equals mc delta T. So what we're going to do is we're going to work out the energy transferred first. And I've left that up into the corner so that you can do it yourself if you want. So please stop the video and do it yourself if you would like. So if we then look at Q equals mc delta T and we just go, there's your equals. We know we've got our mass, that's our mass of our water, which is down here, which is 100. Okay, so that's 100. Okay, so we have 100 and we times that by the specific heat capacity, which is 4.18. And we times that by our temperature change, okay, which you'll just put up here, which is 36.5. So we've had our mass of our water times our specific heat capacity times our temperature change. That will then equal 15,257, and hopefully you've put that in your calculator yourself. Don't just watch this, put it in your calculator, do it yourself. Okay, and we've got to remember that that is in joules, okay? So that is in joules. We then go to our second equation that we're going to use, and this time we need to find out the moles, because at enthalpy change of combustion, the units, if I go down here, the units are kilojoules per mole. And it wants us to determine the enthalpy change of combustion to 4 significant figures. So kilojoules per mole, 4 significant figures. Now kilojoules per mole means energy divided by moles. When you say per, it means divide. So kilojoules per mole means kilojoules divided by moles. So that's energy divided by moles. So we're working out the energy here, and we need to divide that by the moles. So we need to work out the moles. Now, the question is, what is the moles of? Now, in this case, because we are doing the enthalpy change in combustion of propan-2-ol, then it will be the moles of propan-2-ol. So there's our equation, which is moles of the fuel, mass over mR. So where do we get the mass? We get the mass from here. So it's the difference between that is the mass of propan-2-ol. Now, as well as that, we need the mR. So hopefully, again, stop the video, calculate the mR yourself, try and make it interactive. Now, the mR of propan-2-ol is 60. So then all we do is we go here and we start calculating our mass over mR, which is our moles. So that'll be 0.7620 divided by 60. We've got our number here and our number down here, which we calculated. And then that will equal, okay, 0.0127. So 0.0127. And that is your moles, and that is your moles of your fuel. So we've got our moles of our fuel, and we've got our energy. Let's move on to our last part. Remember, I said that it is the energy divided by the moles. Kilojoules per mole means energy divided by moles. Okay, so there we have our energy and divided by our moles. So if our energy is divided by our moles, okay, we then take our 15,257. Okay, we then divide it, and remember that's in joules. Okay, and then that is divided by a number of moles, which is 0.0127. Okay, and that is our moles. And there you can see it coming out, our joules per mole. So joules per mole, and that's where, so at the moment we've got a joules per mole, we haven't got a kilojoules per mole, but let's fix that in a second. So if that is the case, that comes out as 1201, and hopefully you've put it in your calculator. Okay, 338, and then that's 0.583. Okay, and again, that is in joules per mole. Okay. We then want to put it in kilojoules per mole because that's what the question wants. So I'm going to put it and do that. To do this, I'm going to divide that by 1,000. If I divide it by 1,000, it is, in fact, let's do it in pink, 1201. That converts it into kilojoules per mole. And that is where you'd normally stop and you normally go, oh, okay, brilliant, I've got this right. Okay. No. Okay, you're going to miss out one mark, and that's because this is the enthalpy change of combustion, which means the combustion reactions are all exothermic. And that means combustion reactions must be a negative enthalpy change. All right, so I need to put here very clearly a negative 1201. Okay, and I prefer to do it like this. Just look at your temperature changes. It doesn't matter whether it's combustion or not, it can be any type of thing. We'll go over different ones in different videos. That temperature is going up. If that temperature is going up, then this must be an exothermic reaction, which means it's a negative enthalpy change. And that is the bit that a lot of people miss. So don't make it so that you miss it. Okay? Get all of your marks. And that is how you calculate the enthalpy change of combustion using a fuel burner, copper calorimeter, and a mass of water. We're now going to move on to a question that's based upon the accuracy in terms of the enthalpy change of combustion. And that basically means how close are we to the actual value that it should be. Now, I want you to think back to what we described before. What actually affects whether this is close to its actual true value? Well, the biggest effect is the heat loss, because you get heat coming out here, out the sides, out the top. It really should have a lid on, like a bomb calorimeter, or it should all be in a sealed environment like the bomb calorimeter, but no, all the heat is going from the sides there. Okay, so that's the big thing that limits it. There's also another thing that limits its accuracy, and that is the percentage uncertainty. So, for example, here, percentage uncertainty can be with the mass of the fuel that you're measuring. It can be with the temperature change that you're measuring as well. Okay, so there are different percentage uncertainties here. So let's look at an actual question and see where we can go from here. So in the experiment, the water in the beaker was heated for 2 minutes. I want you to tell me whether the accuracy in the student's calculated value could be improved by heating the water for 4. So I'd like you to stop the video now and actually try to answer the question. I've hinted at it before I've put this on the board. Okay, so have a go. So let's go back to the answers for this. I talked to you about uncertainty. So I'm going to put uncertainty there just to remind you before I go through it. But there's two things I talked about. I talked about uncertainty and I talked about heat losses. So the first thing is it's less accurate due to greater heat losses. So if you heat it for 4 minutes, okay, you're going to get more heat going out, okay, more heat being lost, okay, and therefore it will be less energy transferred to the water, which means your Q is going to be lower than expected because you're heating for longer, so you're going to lose more heat. Okay, that makes sense. Now this is one of those questions where there are two answers, and both are totally acceptable. It's less accurate, or it can be more accurate. It can be more accurate because of smaller percentage uncertainty. Now I told you before I put the question up that, for example, if you heat it for longer, you're going to burn more fuel, which means your mass of fuel burnt will be larger, which means your mass of fuel, if you're doing percentage uncertainty, is this measurement at the bottom. If the denominator here gets larger, the uncertainty therefore gets smaller. And you can talk about it in the temperature change as well. If you heat it for 4 minutes, there'll be a larger temperature change. So if we're doing the uncertainty of the temperature change, the measurement's going to get larger, which means the uncertainty is going to get smaller. And these are typically 1 to 2 mark questions in exams, okay? And they do really stretch a lot of people, and a lot of people get them wrong. So make sure you know them. We're now going to move on to the next question, which is a multiple choice question, which is very difficult for a lot of students. And I'm going to show you an easy and simple way of getting through this kind of question. So it's about the accuracy of the enthalpy change of combustion again, and we have 4 scenarios, which I'll show you in a second, and we want to find out which of those scenarios was found out to be less exothermic than expected. Okay, and which explanation would be correct. So here is our 4 scenarios. Feel free to stop the video and read those. But for now, I'm going to put it to the side and then go through the method of doing it. So the method of doing it is just put the equations out and monitor which bits move according to which scenario. So what does that mean? So what that means is here we've got A, the spirit burner was moved away from the beaker and left on. So it was left on. So it's moved and left on. The final temperature was taken of the water as it was moved. So as it was moved, I took that temperature which goes here. So I took the temperature which goes here and I moved it away, and I continued burning the fuel. That means the mass of the fuel burnt, which is here, okay, that's going to be higher than you would expect. So it's going to be higher than you would expect because you're keeping on burning it. Now if that is the case, and then I go to the moles, and I put a little line by the moles, you can see the number of moles is going to go up. If that's gone up, the numerator, that's going to go up. If that is the case, the number of moles here is higher than you would expect. Okay. And if that is higher, this one is, hopefully you can see it by now, that one is lower. Okay, so that number is lower. Now, remember we apply a negative at this point. So if I say, for example, this was 100 normally, should be 100, but I've calculated here it's 50, and then I just put the minus on afterwards. That means minus 50 is less exothermic than minus 100. So if this has gone down, this number, it's less exothermic than expected. So I can say that when it comes to this one, which is A, that is going to be less exothermic than expected. So if we then take this and we get rid of those, and then we do our next one, and there's nothing to stop you just carrying on doing this. You know, this is the method. The method is very simple, and just go down each of them. So the water was boiled for 2 minutes before the final temperature was taken. So this was boiled. So if you know anything about phase change in terms of changes between solid to a liquid and liquid to a gas, you know that when we go here and we're boiling, it's going to stay at 100. It's not going to go up. That means you're going to be burning more fuel. So if I look here, I'm going to be burning more fuel because I've kept it at 2 minutes. So if I'm burning more fuel, the mass of the fuel will go up. Not only at that point is you would expect the temperature to be higher than it currently is because it's going to stop at 100 because you're boiling. You don't go above 100. You're in that kind of phase change essentially. So basically the delta T is going to be less than you would expect. This has a roll-on effect, which means that Q is less than you would expect, okay? Which means that moles is higher than you would expect. Then we take this down here and we can say Q. So if I go here, Q is going to be less, okay? But our moles of our fuel that's burnt is going to be higher, okay? Which means if this has got higher and this has got lower, this is definitely going to be, okay, lower. It's going to be a smaller number. And this is just about putting things into equation, magnitudes of numbers and things like that. Which means that if I go over to this part here, if the water was boiled for 2 minutes before final temperature was taken, then this again would be less exothermic than I would expect. Now again, nothing to stop you just carrying on and doing it yourself, using this method. Now, we've got that. So, if that's the case, let's do the third one. By mistake, the student used the MR of ethanol to do the calculation. So we've got methanol, used ethanol. So the MR is here, and ethanol has a larger MR than methanol, because we say it's methanol here, which means our MR is going to be larger than we would expect, which means the number of moles is going to go down, which means down here, the number of moles is going to go down. Imagine you're in the exam, you quickly just write out all these arrows. It doesn't take very long at all. And that's lower, which means this number is going to be higher, which means that will be more exothermic than you would expect. Okay, so this is definitely wrong. We'll do the final one. Hopefully you're getting the grip of it now. And maybe you're getting a grip to such a point where you're just going to stop the video because you can actually do it, which would be a great option. All right. Student did not stir and left the thermometer by the heat. So the thermometer is right there. It's by the heat, didn't stir. That means it's going to be hotter here than it is everywhere else because you haven't stirred it and everything like that. That means you're going to get a false temperature change. So this is going to be higher than you would expect. If that's the case, that's going to be higher than you would expect. If that is the case, this is going to be higher than you would expect. If that's the case, that number will be larger than you would expect. And again, when you put the minus on, that means it's more exothermic than you would expect. And so if we go down here, we can say that that is totally wrong. Okay, so what we've done here is shown you 4 examples. There can be different examples. For example, incomplete combustion. They say there's incomplete combustion. Well, that just means less energy is transferred to the water. Okay, but there could be other options that they can choose here. We can't show you every single last option, but what we can do is show you the method, just track the numbers through, and then what you'll do is you'll realise what happens to the enthalpy change of combustion, and you can answer the question. And if you're doing it on your own, okay, without me talking through it, you could probably do it quite quick. Okay, so hopefully this has shown you exactly how to do this style of question.